Okay, lab class. This is the module or video for determining the intensity of a diffraction peak for a single phase. So you might be able to tell that this is actually from one of your MSE408 videos. So in there, I talked about the integrated intensity is equal to this expression. So we have the structure factor, which we've talked about before in the lecture class, the 585. So this is something that we should be able to calculate. We have the multiplicity factor, P. We have the Lorentz polarization factor, which is, as you can see here, a function of the value theta. And then we have the temperature factor, which is also a value of factor of theta, but we just give it as one term here. So we have structure factor, multiplicity factor, the Lorentz polarization factor, or LP, and then we have, lastly, the temperature factor. So to be able to solve for a given intensity of a peak, we need to be able to solve for all of these. And so obviously this is an excellent opportunity to use a spreadsheet like Google Sheets or Excel. And so next, I'll go through each one of these and hopefully guide you on how to either solve for it or find the value. Okay, so the first term that we saw from the equation there was the structure factor. And so the structure factor for a given set of HKL planes is a summation from N to capital N. So we're counting up atoms or ions or molecules, and that's equal to the atomic scattering factor, Fn, so of the particular atom that we're looking at, times an exponential term of 2 pi I, the imaginary number, and then H times UN plus K times Vn plus L times Wn. So the coordinates UN, Vn, Wn are the location of the atoms for N, right? So basically the location of the N atom. So that's why we have a summation, because we could potentially have multiple atoms in one unit cell. And then the HKL are obviously the Miller indices for the given set of planes. So we can calculate this for a given structure, and a lot of times these have been calculated for us. So feel free to look up references if you get stuck in the structure factor calculations for your given structure. So the last part of this, so we should know where the positions are from looking at the unit cell, and we should know what the planes of interest are that we're looking at. And so the last part is going to be this atomic scattering factor. And so these are tabulated. So I'm going to switch over and show you how to find these atomic scattering factors. All right, so this is Appendix 10 in the Cullity text. While you don't have access to the full book, I have put selected portions, and sorry for the zoom here, I have put selected portions of this, particularly the appendices, because they are good references in your course Canvas page. So you should be able to find this in the Canvas page for this lab and look at for the PDFs with Cullity in them. So we can find this, and what you see here is that along here there's a number of different atoms, and then you can also find select ions. And up here is the sine theta over lambda term, which is common throughout these calculations. So you'll want to calculate that for your peak. And then basically this gives a tabulated value for the atomic scattering factor of a given atom or ion at that given angle. So it's angle dependent as well. So you can use these values. You might, if you're not at 0.1 or 0.0, 0.1, 0.2, etc., you might have to interpolate between these values, but this is a good starting point to determine the atomic scattering factors. So you'll need this for your structure factor calculations. Okay, according to our equation, the next thing we need to talk about after structure factor is this multiplicity factor, P. And so this is the number of permutations for a given set of HKL values. So this is something that you could calculate if you want, looking at the different permutations you can find for your HKL planes. But also it is tabulated. So that's the good part here. So again, going back to Cullity, this time appendix 11. So this is the multiplicity factor for powder patterns. And you can see here that it gives you not only for cubic, but other structures as well. And over here, it gives you the type of plane it is, and then the multiplicity factor below. So if it's a generic set of HKL planes, then the multiplicity is 48. Whereas if you have a type where it's HHL, meaning two of the values are the same and then the other one is different, then that is 24. And then it has other values for zeros and other combinations as well. So anytime you see a multiple, for example, the second one says HH, that just means that two things are the same. And then the zero obviously means zero. So that's kind of how you read this. And below it, you get the multiplicity factor. So that's how we can get the second term. Okay, so going back to our equation, we've figured out where to get these values and these values. And now let's look at the next one. So this Lorentz polarization factor. So this one's the easiest to do, I would say. You're given the equation here for what that is, and we can simply plug in the theta values and calculate this directly. So I recommend doing that. If you want to check your work and just make sure that you have the correct values, they are tabulated as well. So if I go to Cullity again, the appendix 12 gives you the Lorentz polarization factor, and you can see it's the same expression that we have. Just double check it. Yeah, so it's the same expression. So again, if you're checking your course textbook for 585, I think there's an error in that expression, but you can calculate and you can compare to here. So here it's tabulated, so you'll only get certain values of angle here. So you have to kind of be able to interpolate a little bit if you need something slightly better. So it's here if you want to sort of double check your work. Okay, so lastly we have the temperature factor. So here, as in a lot of things, it's tabulated. So if I point your attention to appendix 13 this time, you'll see a data table for the temperature factor. However, we really haven't talked about this up here. So if you want to, you can kind of investigate that further and use this table. But also, maybe slightly more convenient, is in your course textbook for 585, you'll notice you have figure 2.27, and this is the temperature factor as a function of the angle. So similar to that table, but here it's a lot easier to read. So you just have to calculate sine theta over lambda, and then you can approximate the value from this figure. So I might recommend that you blow this up and kind of visually get the temperature factor from the inputting the angle and reading off this graph. I've kind of just done this in a basic computer program where I can kind of draw some lines and interpolate where a given value is for the temperature factor. So that is reasonable enough. So if you have values like 0.95 or 8.3, those are close enough for the temperature factor calculation. All right, so that kind of takes us through the intensity factor, the intensity for a given peak where we have structure factor. We've gone through and shown how to do this, the multiplicity, where to find that, how to calculate or find this, and how to calculate or find this. So there's a lot of information here that I would definitely input into a spreadsheet, but you'll want to do that for all the predicted peaks of your pattern in order to determine the relative intensities. In this case, the integrated intensity, which, if you need a quick refresher, is the area underneath the curve. Under the peak. So that's how we find those values for intensity, and that's how we can predict single phase intensities.